Welcome to the webinar series of Computer Science Department, Jyoti Engineering College. So today we have the title ZETTABYTE and Beyond. And we got our resource person, Mr. Tomy AC. He is the solution architect of Global Sales Engineering, Hewlett and Packard Enterprise. With this, I would like to welcome our resource person to the webinar, and also I would like to express deep gratitude to my management of our college and also our department for making happen this program. We got nearly 300 registrations, and so far nearly 100 participants already logged in with this system. I think remaining people will be joining within a short while. So we have our resource person. He's from industry. Of course, he has a 17 years experience in various server and storage related technologies, and he was associated with various companies including NetApp, SanDisk, Western Digital, and he is currently working with Hewlett Packard. He holds multiple patents in the field of storage systems and have contributions towards open source initiatives. So with this introduction, I request our resource person to start the session. Thank you all.
Thanks, Binish, sir. Are you able to hear me?
Yes, sir. Here.
Okay. The slides are visible?
Yeah, sure.
Okay. So good evening, students and respected faculties. And I think someone from industry is also joining. So welcome to this particular session. And this is basically a deep dive session on the state of data storage currently. Okay. So we are going to heading to ZETTABYTE. We are already in ZETTABYTE, and we might be progressing to more than ZETTABYTE. So let's see how these things are we achieve, and going forward how it will be. So we will see some of the basics of storage and how we are going to progress. Okay. If there is any disturbance in video or anything, let me know. And if the slides are not progressing also, let me know. With that, let's start. So storage, everybody needs storage, meaning this is a pandemic situation. So probably all of you are safe at home. I hope so. And all of us daily, we will be seeing this COVID-19 dashboard, right? I'm pretty sure about that. So that's some amount of data point which is being collected and processed. And similarly, currently we have some issues with our neighbors, and we just banned the video platform called TikTok. You have any idea how much is that costing basically? So it's around $6 billion. So can you imagine that? And in our state also, we had lots of controversies around data privacy and all other things, right? Very recently. So all these things are pointing to one thing, which the economist is telling recently, that data is the most valuable resource in this world right now. With that, let's start. So in order to see anything, I mean, if you want to improve anything, you should know how exactly we reached here, right? So let's see that. So what we are trying to do here, we want to emulate the human brain, right, and our interactions, and basically we want to make our life much more easier, right? So what exactly is human brain? So according to the Scientific American, it's almost, the memory capacity is around 2.5 petabyte. Okay, so that's how many zeros? You can just try it out, right? It's 2 power 18. So what's the problem with brain? It's a very good storage system, but what's the problem with brain? So the basic issue with brain is it's a temporal kind of storage system, meaning you will actually have some kind of storage, but you tend to forget it. It's not persistent. It might be persistent for some kind of your memories, but not for all. And the other basic issue is that it's not portable. Whatever you are thinking, it's not transferable to another person. So in each of this journey, we should try to see what is the problem and what is the solution. So that's the next step basically, right? So then we progressed into more persistent kind of storage where we started writing in rocks and all, right? But again, the problem still persists because writing into a rock, it's kind of very inefficient, meaning you need hard tools to write to that, and there is no enough space and all, and it will be mostly in some pictorial manners. So still it's not portable also, and very low capacity. So what they did, they started doing tablets, clay tablets. They started writing in hieroglyphics and similar things. Now it's portable, but the management is not so easy. Then what happened? Then we started with papers. What's a good thing with paper? So it's portable. You have lots of paper available. You can write so many things. All these things are possible, and you can keep it in a very managed way. But what's the problem there? Sorting and searching. You can still sort and search, but not so efficiently. Then we thought about, okay, let's employ machines to do that for us, right? So what happened is that we invented a computer system, and computers knows what? Ones and zeros, nothing else, right? So how we program them? So basically we started writing things in format like ones and zeros, and that's punched cards. And what's the problem with punched cards? Again, management is very difficult, programming is very difficult. The entire thing, if there is one error in punching a hole, you have to discard the entire paper, right? So then we figure out, okay, let's have some kind of electronic medium where it is easy to program kind of. So that's a picture of the first hard drive, which is getting loaded into an aeroplane. And you have any idea what's the capacity of that hard drive? It's just 3.75 MB. That should be equivalent to one photo what we take these days, right? And what's the cost of that? That's the major thing. That particular thing was sold for $3,200, and that's actually a lease for 1 month. That will be around almost $30,000 today. Okay, so that's pretty expensive for such a amount of storage. But from there we had zoomed pretty fast. This is around 1960s basically. From there we zoomed pretty fast. We had floppy drives, we have tape drives, we have optical drives like CDs, DVDs, Blu-rays, hard disks of various kinds like speeds and capacities, NAND, USB drives, micro SD cards, SD cards, and all kind of NAND devices. And now we reached at a state like we have persistent memory as well, right? So this is something about past. And now what is happening? Now basically we have a pyramid. We have a hierarchy of devices, and each device is like a cache to the previous layer, meaning we have hard disk layer, which is of storage, and obviously we have tape layer also, and that is kind of pretty cheap to use, but the kind of latencies, it's around millisecond kind of. That's not acceptable for a CPU. You might have already read in your computer organization and architecture that CPU, what CPU does, it fetch and execute, and what it fetch, it's data, and CPU runs at nanosecond speed. And if you are giving data at millisecond response time, CPU cannot progress basically efficiently. So what you do, you cache it. You cache it in memory, but memory is pretty expensive. So what you do, you keep another layer, which is kind of cheap, but a little more better latency, which it provides, right? So we have a hierarchy of storage things, and now it is getting merged into memory kind of system. Like with the newest NVDIMM, that's actually the merge of storage and memory. So you can use such system as memory as well as a storage device. And what's the basic difference there? Memory is basically accessed in terms of bytes, or 8 bytes basically. You know already what it is, right? But block devices are accessed in terms of blocks, which is multiples of kilobytes or something of that sort. It's a much higher abstraction. So that's the basic difference between memory and storage. And now we will see what are the different access mechanisms we can access the storage device, the basics of storage. So if you see, there are three basic kind of storage access mechanisms today, and whatever other kind of mechanism we want, we can always make it on top of this basic access. So let me introduce the trinity of the storage. Basically, the first one is obviously the block storage, and second one is the file storage, and third one, and this is kind of the newest one, which is the object storage. So these are the three main methodologies of access mechanism to any kind of storage. Let's see each of them one by one. Let's start with the block device, which is um, pretty old. If you see the hard disk era, the block disk kind of access was the one which we started with. So what exactly is block access? So imagine your hard disk as a box, which is I had given shown in this orange box, right? So your entire capacity is there in that storage. Imagine that you want to write some, let's say you want to update one photo file into that particular device. How you do that? You have to access this entire disk space and change that particular file of that particular image in that particular block and write it back. If it was a small device like the hard disk which I showed, like that 3.75 MB one, that should have been pretty easy because it's just 3.75 MB. But imagine the hard disk what we have today. It's much bigger than that. Like terabytes of capacities are available with each hard disk. So it's not that easy. So what you do? So basically, you do divide and conquer. What you do is like you split that entire space into multiple blocks, which you can manage easily. Now the problem is resolved. You can write in terms of blocks and read also in terms of blocks. Let's say if you want to write something to block number 6, that's pretty much easy. You are not going to touch any other blocks other than 6, right? So that kind of management is easy. So this is basically the block access. It sounds pretty simple, but it's not. How? I'll just explain. So basically, the devices used for block or any kind of storages are either hard disk or SSDs these days. So hard disk are basically the spinning media, which the mechanical parts it have, and SSDs are basically NAND devices. There is no mechanical part, but still you have to manage the device. Because this hard disk, you have sectors, cylinders, and those aspects. It doesn't know what is a block. So somebody need to convert that aspect of block into sectors and cylinders. Basically, who does that? The firmware inside the drive does that. So that's one software aspect of it. And on top of that, these devices need to connect into the system, right? So who is going to do that? So basically, there are interfacing mechanism, serial ATA, SAS, and latest one is NVMe. So these are the interfaces which connect this particular device into your system, and it uses some protocol, the predominant one being SCSI, okay, which is small computer system interface. And there are limitations for these interfaces. As you can see, serial ATA is kind of saturated at 6 gigabits per second, and SAS is basically running at 24 gigabits per second, and NVMe actually it can touch terabits per second. So on top of this, you have network protocols, and these are the network protocols which we use in industry these days. You can go through that. Probably I'm not going to explain this in detail. Then on top of that, we need to, okay, so in your laptop or a computer, your hard disk or SSD is within the system. But in industry, that's not the case. You will be sharing this particular space, right? So you will keep it in a common place, and your host systems, I'll just explain in a bit, will be connected into those shared storage using these kind of transports. Basically the fiber channel, or you can use the Ethernet, or there is InfiniBand. There could be other kind of systems, but these are very predominant. Let's see, there are two kind of block accesses. One is the direct attached storage. Examples are your laptop or your desktops or SMB servers. So what it have is like it will have number of disks inside that, and probably you can create some RAID mechanism on top of that. So RAID 1 is basically mirroring. where even if you lost one device, still you can access your the data because it's mirrored, right? So that kind of protection mechanism can be inbuilt, and that's your hardware layer. On top of that, your operating system will have device drivers which will be converting the user requests into the device specific things, right? So that's another software part. And basically most operating system will have the block subsystem, which will be converting your abstracted block system reads, writes, and other things into device driver specific things. And on top of that, you will have your block abstraction. So in case of Linux, you can see /dev/sda sdb, like that basically. So that's the abstraction what is given to you. There is some disturbance in the line. Can okay, thank you. Okay, so now you have storage area network array. So this is the one which we will be using in industry widely, and it will have a controller, generally a dual controller for high availability purpose, and each controller will have disk ports and host ports. Host ports will be connecting your storage into the host machine where your block devices can be accessed, and the disk port will be connected to your disk drives, a lot of it basically, where you will be creating something called LUNs. Okay, so that is the logical unit, which is very equivalent to your hard disk or anything, but dynamically allocated basically. Okay, so this is the abstraction of storage area network array. And how does it look like? So this is one SAN array which HPE is providing. This is called Primera. This is our tier 0 solution. So this particular storage SAN array will be connected to switch basically. So this is a typical deployment model. So you'll have multiple switch for high availability. You might be thinking why there is only one SAN array. It has already 2 controllers for HA, but there is a possibility that this SAN array also can go bad, right? So we will see that in a bit. Just right now, you imagine that the high availability is given by this iSCSI or FC switch. Now it will be connected using FC cable. Then the host system where these block devices will be accessed also will be connected to the switch. Now in the host system, there might not be any hard disk at all. There might be hard disk for the operating system for it to run, but otherwise no other storage might be available. Now the storage system, host operating system, will be accessing this particular LUNs which are created in the SAN array, which will be having worldwide name, which is a unique ID. You will be using that to show it in your for your operating system to use. Okay. And you can have multiple hosts connected to the system, and they can share the LUN or they can access multiple LUNs from the same SAN array. So the problem solved here is that the shared storage, which cannot be done from a single system. Let's move on to file. File abstraction is pretty simple. Simple idea. You have a root directory. Now directory can have subdirectories or files. That's a simple abstraction. So you can have subdirectories or files, and subdirectories again can have files or subdirectories and files. So like that the tree grows. So this is basically your tree structure which you had already studied in your algorithms. Now there are 3 different kinds of file system deployment possible. One is a standalone. Basically your laptop is a good example for that, but in industry you will be using servers. So servers will have an operating system. Operating system will have, you have to use a file system, and file system will mount, and you will have your hierarchy from root onwards to wherever you want, right? Examples are ext2, xfs, btrfs, ntfs. So ntfs is the Windows file system, and others are basically the Linux file system. So this is standalone way of deploying it. Second method is clustered and distributed method, where you have multiple systems with its own operating system, and that will form a cluster. And on top of that, you will deploy a file system which is across all the systems, meaning it's a single system image. You write something into this particular file system that will be visible to all the 4 systems. Okay. So this is a kind of networked file system, but only in a closed loop of the cluster, right? So you can create directories or files on top of that file system. And examples are Lustre, CXFS, VXFS. So Lustre is generally available in open source. And the third type is networked file system. So basically the client server architecture. So here, the problem with clustered file system is basically you cannot share the file system outside this cluster, right? But if you want to share, meaning heterogeneous kind of systems, meaning you want to share the same file system with Linux, Unix kind of systems, that's not possible with this cluster file system. So you have a client server model in network file system, where you will we will see that in a bit. Examples of the protocols are NFS, which is network file system, SMB, server message block. And how network attached storage is deployed. So basically, this is an example of scale out NAS using HPE Apollo 4200 systems. You will have file system on top of that for all the machines basically. Then you will have NFS or SMB exports basically. So we are not going to access the file system here. We just export it. Now it will be connected to network switch, which will be indeed connected to a host where the file system will be used. And in host, you will have operating system. Then there will be a mount point. So according to your access, you will mount this NFS or SMB exports over there. Bingo, you have your file system there. So similarly, you can have multiple hosts share this file system, or new file system you can create. And coming to object storage, which is the third kind of abstraction. So what's the problem with file system? You have hierarchies, right? And you can have very limited number of metadata. So in object, that problem is kind of resolved with a flat namespace, meaning you don't have any hierarchy. Any object in that system you can directly access. How? So you can have object of any size, any shape, any color, anything. Only thing is that it need to be uniquely identified by an object ID. Okay, so that's the only thing here. Object ID, you access the object either for read or write, for any other kind of access. And similarly, you can have trillions of objects in the namespace. Okay, so this is an abstraction, and generally to hold these objects you will have some abstraction called bucket, which is not, that's just a virtual abstraction. There is nothing physical, just a container for all these objects to hold together. And other than that, it's a flat namespace. And how it is deployed? So basically there will be a scale out object storage system, and you can access from anywhere. You don't even need a host. You can access it from a web browser also. And predominant protocol used here is S3. Okay, S3 is not the S3 storage with the cloud service provider gives. This is an S3 protocol. And S3 protocol is a request response system. And what does it mean? So basically you give a request, like let's say I want to write an object. You say put my image.jpg in your web browser. So according to the web browser's settings, it will create the request headers basically, and you can see the contents of the request header, and it will attach the stream of bytes of that particular object also. And now that goes to the object storage system. Now you will get a response back, and the response header will have many information which is relevant to that particular data. So this is pretty simple and highly scalable. So now we had seen all the three storages. Now we will see how we select a particular kind of access for a particular application. So the key metrics which we consider, first one is bandwidth, starting from megabits per second to terabits per second. Second metrics what we check is capacity. What kind of capacity we need? Ranges from gigabytes to exabytes. And multiple exabytes definitely forms the zettabyte. And the third one is latency, which ranges from microseconds to milliseconds. Let's see how these access mechanism spans across these key matrices. Block system, if you see, it's very high latency and average bandwidth and very low capacity. Okay, so in these kind of scenarios, the block system access will fit in. And file systems, it's all are average. Basically you will get average latency, average bandwidth, and average capacity. Scalability is possible with file system. With case of object, it's another case. It is built for very high throughput and very highly scalable capacity levels, but the latencies could be huge. So these are the main things for the object storage system. And let's see where these things are used generally in a mission critical systems like databases or OLTP kind of tier 0 tier 1 applications. Block systems will be used, and file system generally used in tier 2 and tier 3 where latencies are okay, not so high, like backup or file share kind of activities. And object is the reason one latencies are high, but it can handle a lot of capacity, so it will be used for big data, AI ML analytics kind of workload, basically the OLTP kind of workloads and big data kind of workloads. Another major factor which determines the access is the dollar per gigabyte. So basically you have to buy these hardware systems, right? So you will see what's the cost associated with that. Okay. And another aspect is dollar per IOPS. For each IO you are doing, how much you are spending. And another aspect recently people are looking at is kilowatt hour per GB. That's your energy consumption. So these are the key matrices when you see before selecting a kind of storage for your particular application in industry. So let's see some of the industry enterprise features. Okay, I'll go a bit fast on this. But still, so reliability is the utmost feature which is required for industrial systems. So first thing is self-healing. As I said, RAID, hardware RAID. So you can see 4 data to parity and 1 spare disk. Basically imagine that yellow ones are the disk in a particular system, and that particular system failed. Now what you have to do, you have to reconstruct that particular data, right? So you have to move all the data from yellow to the gray one. If you do that, it will take a lot of time because it's between 2 systems, right? So your RAID reconstruction time increases. What if the orange parity disk also fail? Now you are in trouble, right? You don't have any more protection. So that's been solved by distributed RAID, which is extensively used in software defined storage, which we will discuss in a bit. Now the entire data and parity is distributed across your RAID, software RAID. And even though a system where marked as X fails, we will be using multiple systems to do the reconstruction, and the reconstruction time drastically reduces. And another good feature is snapshotting. What is snapshot? Let's say you have a block or file system. Let's say let's take the block system. You have ABC written at any point of time in a block system. Now you take a snapshot. Snapshot is nothing but a photo of that instance. Now you take S1, you will get A, B, and C in that particular snapshot. Okay. Now, as the time progress, you might modify C to C dash. Now, at that point of time, if you take a snapshot S2, you will have A, B, and C dash, not C, because C is already modified to C dash. But why C is still there? Because the snapshot is there. And what's the use of snapshot? If you reached at a state at S2 and you just remember that C dash is not the one what you want, then if you want to go back in time, you can do that. You can just delete snapshot S2, then you will go back to ABC basically, right? Similarly, you can take write another block D, and you can take a snapshot S3 will be pointing to A, B, C dash, and D. Okay. And where snapshots are used? Basically for backup and cloning features basically. And security, at most for reliability, and security have different aspects like data protection for in transit data, because as I said, you have a storage system and a host system. So, and between that there is some kind of wire, right? Either FC or Ethernet or anything of that sort. So data will be moving through that wire, and obviously you know that you cut the wire, you connect to a system in between, you can actually snoop into that, right? So that shouldn't be possible. So for that, you need some kind of security. And inside system also, just imagine that somebody took your server hardware and want to use the data inside that. It's pretty much possible, right? So in order to protect that, you need to encrypt your data at rest. So you'll be using SSL, AES encryption, RSA encryption, all these things. And another thing is that you need to authenticate users or applications into your system. You cannot just simply connect it to network and everybody can access the system, right? So for that, you will use authentication. We will be using Active Directory, lightweight directory access protocol, Kerberos, those kind of aspects. That's all industry standards. Then once you identify it as a user, now user should have some privileges also. Okay, so user can use so directories or blocks, not others, basically, right? So for that, you need to have authorization. And authorization, you can use role-based access control. A simple mechanism is there in your Linux system, that is your file permissions that read, write, execute for user group others. That's the simplest mechanism. On top of that, you can have ACLs, ACEs, RBAC, all those things. Another important part is auditing, because these days data privacy and data compliance are at most importance, right? Because compliance, you might have heard about SOA, HIPAA, FCRA, GDPR, these kind of data privacy laws also you might have heard about, because industries need to keep the data essentially for financial or healthcare verticals for so period, ranging from 3 years, 7 years, 15 years. You have to keep this data. So auditing is important. You should know who added the data, where it is going, who deleted the data. So basically logging, querying, reporting, basically. So let's see the availability features. The first availability feature is replication inside the system. What is replication? Let's say the client writes something into host. Okay. Now host will have the data and it will be written into one disk drive. If that disk drive fail, what will happen? The data is lost. But that's not the case what we want, right? So what we will do in replication is, we will have something called replication factor. In case of replication factor 3, meaning you will write into 3 different places the same data. But what's the problem? Now you have to have 3x space utilization. Imagine 1 terabyte data is written by client to host. Now that translates through 3 terabyte data into the drives, basically. So the effective capacity reduced by 1/3. But you will get 2 failure kind of availability. So to counter that, we have something called erasure coding. Erasure coding, what happens is that when client writes something into host split that into that many pieces, which is m plus n. M is the number of data chunks and n is the number of parity. Here it's 4 plus 2 what I had shown. So it will be written into 4 plus 2, 6 places, basically. Now what's the good thing? Now you write 1 terabyte of data, it will be split into 4 and you will be adding 2 parity chunks into that. So effectively you will be writing 1.5 times of data into the system. So there is a savings here, but still there is a 0.5% 5 overhead, 50% overhead is there. So these are 2 availability things. And disaster recovery. Earlier I told, like, let's say you have a storage system. What if that storage system, it got failed, right? What you will do, basically? So essentially you cannot do much because your entire system is gone, but generally that shouldn't be the case. Imagine the banking system. Let's say some disaster like a flood or something happened and all your data center is gone. Banks cannot say that I don't have your data anymore because it's your money, right? So what generally in such situation they do is, like, they will replicate the entire system into a different system altogether. There are multiple ways possible. This is called mirroring, and it can be from production to test over a LAN system. LAN is your local area network, or from an active site to a DR site, 2 different data centers over a wide area network. It could be across country or across globe also. And other possibility these days is, like, you can do backup from on-premise data center to a cloud data center also. This could work out cheap in some cases. Some cases availability is also good. And two things to note here is recovery point objective and recovery time objective basically. And what are those basically? So recovery point objective is like you cannot transfer the data from site 1 to site 2 at, exactly at the same time, right? If it is pretty fast, your round trip time need to be considered, right? In that case, your client write latency will go high. In that case, what you do is like, you will take a snapshot at some time and then you transfer that differential data to the remote system. What's the catch there? You take a snapshot and after that whatever data is written might not be backed up to your DR site. But you can do a synchronous mirroring also, but you have to be very very considerable about your latencies. So that's your recovery point objective, meaning how much amount of delta of data you are okay to lose. Okay. And RTO is basically recovery time objective. It's like basically, let's say your primary site is down, how fast you can make your DR site up and running. Serviceability is another aspect. So basically you might need to upgrade. Maybe you started with some amount of data and some compute power, but later if you want to process more thing, you want to add more compute. So how you do that? Probably you change the controller, but in place data support should be there for that system. Multi-tenancy, you might have big data center, but that said data center might be shared by multiple companies. Typical example is sharing by Coca-Cola and Pepsi, meaning they might be rivals, so each other's data should not be seen by each other, right? So lots of restrictions you need to put into your systems. So that's called multi-tenancy. And quota, like let's say you have so much of data, but you want to limit the data access by certain user. Even in your college also, probably you might have shared disks where you want to restrict the data access to certain user. Let's say every student can access 10 GB of data, not more than that. Maybe the faculties can access around 20 GB of data, not more than that, something of that. How you do that? You enable quota. So you will have warning quota. These are all configurable, and limit quota. And beyond that, you will not be able to write anything. Scalability, there are two aspects. One is scale up. Basically, you start with a small system, you want to increase your capacity. So in the same system, you add more disk drives, basically. So that's scale up. And if you want to increase your computing power, add more computational power into your controllers. So that's scale up within the system. And there is scale out. Scale out is basically if you want more capacity or computational power, you add one more system. So that is scale out. And storage efficiency, compression is there. Lossless and lossy compressions are there. Lossless means you have original, you compress it, you get a small data, and you decompress it, you get the original data. Examples are LZ4, Snappy algorithms. Lossy algorithms, your original compressed, you get a small one, but you decompress, you will not get the original, but that's okay for some aspects like JPEG, MPEG, MP3. Even if there is some distortion also, you will not be able to notice it, right? And there is deduplication. Deduplication means the client starts writing something. Okay, let's say you write a yellow file. Now host doesn't have it. Now host will accept that write. Now you write more yellow files. Host already have the yellow file. Why you need to write more, right? Since whenever the client asks for a yellow file, you can already get it from the host, right? So no more writes of yellow will be done. Similarly, for any other color, you do more. So I put color as a representation here, but generally you will do fingerprinting of the data blocks basically. So like that. So as you can imagine, as you grow, the deduplication can be very efficient in case you write a lot of duplicate data. And tiering, of course, very important thing, because SSDs of very low latencies are very expensive. So you want to limit that. So you keep your hot data in such tier. And once it becomes a bit warm, you send it to a different layer, which is warm. then it might become cold, and then it might become frozen also. So accordingly, your cost will reduce, your latencies will increase. So whenever CPU want to access something from frozen layer, then you have to read it from frozen layer, bring it to hot layer, and then access it. So all the caching algorithms work here, like write through, write back, all these things applies here. Manageability, that's another part. Basically, your system, that's a centralized system, it has to be managed either by CLI, which is your command line interface, which is generally used by system administrator. If you want to use some graphical user interface, that should be available. And the reason one is not graphical or CLI, generally we use REST. So basically, just like that S3 thing, it's a request response system. It's highly programmable. You can customize basically. And now, so far we had discussed about hardware or system defined storage. It's very tied to hardware. Now we will see software defined storage. And what exactly it is, it's an evolving definition. So basically, you want to, two things what we do with storage is basically, one is provision and one is manage. Provision meaning you allocate some space. Manage means who uses that, how uses that, all the policies basically. So these two things in an independent way from the underlying hardware. It shouldn't be depending on any hardware or any vendor basically. So there are various kinds of software defined storage. First one being unified block file object. So far we had seen block file object from different systems, but it can be unified also. Another is scale out. Basically, in a software fashion, you can have block file and object. Various combinations are possible. And the third kind is hyper converged infrastructure, where you have systems where storage and compute is there in a hyper converged way. And there is a new way which is disaggregated hyper converged infrastructure. Example is HPE Nimble system, where you can actually increase your computational or storage independent of each other. So hyper converged example is HPE's SimpliVity. And there is storage virtualization also. So this is basically whatever we have seen so far in a hardware system. That particular software itself in a virtualized way is available to you to run on any bare metal or mostly on virtual machines, and you can access different hardware. So that's storage virtualization. We will see one unified block file and objects software defined storage next, which is Ceph. This is an open source software which is readily available. You all can go and access the software code as well. Let's see the architecture, how they are achieving this. So basic thing is something called OSD. This is nothing but your Linux system with some storage in it. And on top of that, they have we need to use something called monitor nodes, which will monitor this particular cluster. MDS is metadata server, that's for file system metadata. And management node, of course, for your CLI, GUI, or REST API access basically. So these are all softwares, no hardware involved. Only thing is that is OSD need to be attached with some hardware. Now they had written a layer called RADOS. This is an acronym for Reliable Autonomic Distributed Object Storage. So this particular software layer do the magic. They convert whatever coming from top into the OSD levels. How they do that? They had written a library on top of that. This is as good as your shared library, librados it is called. You can compile with any of your applications, and there are pre-compiled applications as well. And the abstraction below RADOS is basically something called pools. It's a collection of something called placement groups, where you place your data in your OSDs basically. So you can have replicated pool, or you can have erasure coded pool, which we discussed a little earlier, right? So this is very important. The placement algorithm is very important. So with on top of this, what you do is like this particular librados can be compiled. It's a pre-compiled application which is called RBD, RADOS block device, which will give block access to any host basically. Similarly, they have something called CephFS, which gives file access. and there is something called Rados gateway, which will give object access from the same system, and all these kind of access coexist in the same system. How is that? We'll see. So host can access your block, clients can access your file using NFS SMB, objects, any apps can access your objects using S3, Swift using RGW. Or one more thing, an app can directly access your system as well using librados library. You can use those APIs to access the storage. And how they do that? They use something called an algorithm called crush, which is controlled replication under scalable hashing. This is a way of consistent hashing which is extensively used in software defined storage. It could be different for each system, but in Ceph they use something called crush. So app will calculate according to the crush and the data available in monitor nodes to figure out which PG to go. From there, the PG knows which OSD to go. So that's your primary OSD. And if it is a write, probably this is coming from a replicated one, it will go to 2 more OSDs. So even one OSD goes offline, doesn't matter, you will have your data. Similarly, erasure coding pool, you will write into 4+2. If it is a 4+2, you can have 15, 5, all these kind of combinations are possible. One thing to note here is that you can see in this particular OSD, you have coexistence of erasure coded data as well as replicated data. And how it is deployed? Okay, so this is one example. So you have HPE DL systems having MDS and monitor nodes. Monitor for high availability, generally you will keep 3 or multiple odd numbers basically. And management, you have 1 node. And OSDs, you are keeping in HPE Synergy frames basically. You have a compute and storage there. And you have private network for internal data movement and public network for external data movement. Now, any from management network, you can access your management features, and any bare metal or virtual machines or containers or web can be connected to public network to access any of block, file, or object from this particular system. And if you want, let's say your file system is choking, you want to add more, you can add 1 more MDS, or like that you can add. Or if you want space or capacity, you add more OSDs basically. That's pretty much possible. So that's about storage, software defined storage. Let's see some of the trends which we're seeing in the storage space now. So we have in Linux or any storage system, we have this block subsystem basically. It's time to rewrite that actually. Most of you might have seen that Linux and all is kind of abstracted out, but still at times we want faster storage, right? What's the use case for that basically? So earlier you have spinning media. If you see the latency, that's around 1 millisecond. I had shown 100 because otherwise it will add complexities to this particular graph. Generally it is in millisecond latency, but if you see that orange colored is the latency used by your software system, like your drivers, your block subsystem, or user space even. So that's around 10 microseconds, sorry. So if you consider that, considering the spinning media latency, that software latency is comparatively less for spinning media, meaning 100 or 110 doesn't matter, right? But you consider the latest media like NAND, SSD systems, where your drive latency itself is in 10 microseconds, and if software itself is adding 10 microseconds, that's huge. That's 100% overhead, right? So you will be bottlenecked in your software. So that's a very good use case to look into rewriting the storage. So with the latest NVMe stack, what we have done, industry has done, is that they had cut so many of these layers basically. So you can see in this particular diagram, the NVMe driver is directly accessing the PCIe root port. There is no other layers in between. So that actually cuts a lot of latency from the software. And now there are user level NVMe drivers using DPDK or SPDK, those kind of programming models, and you can still reduce the latencies. And the other aspect is that earlier you can see the SATA device stack. There is a single request queue with a spin lock. That could be a big bottleneck over there. but now we have multiple queues with NVMe stack. There is um, there are different queues, submission queue and completion queue, one for admin and for IO. For IO, theoretically you can have 64k queues, and this actually speed up your asynchronous access. Now, the other major thing happening right now is the persistent storage field, basically. And what is that? You might have heard about containerization a lot these days. So, what are the characters in a typical storage system? Basically, you have storage admins who manages the storage systems, and you have application users who will use the particular storage. And generally what happens is that whenever user requires some amount of storage, it will request the storage admin. It's like a red tape process. A storage admin will take their own sweet time to provision the block or file or object buckets basically to the user, and then user have to wait for that. So your deployment take time, right? But in an agile world, that's not acceptable. So now the user storage admin, basically he manages NAS or SAN systems, and user will use containers which will have pods. Basically, if you are familiar with Kubernetes, you will have pods over there which will require persistent storage to have persistent applications. So in SAN system, definitely you will have FC or you have iSCSI storage, basically the LUNs. And NAS, you can have NFS or SMB exports basically. So storage admin basically manages that. Now the good thing is that you can have persistent volumes, generally using CSI drivers in Kubernetes world, and you can have abstractions of persistent volume on top of that. Now you can assign a specific capacity to that and forget it. Now user, he or she will come through Kubernetes orchestration mechanism. He or she need not go to the storage admin directly. They will access the storage space and they will provision it, they will manage it, and they will use it in their pod. And storage admin is relieved from those tasks, and user is also happy. They can deploy it pretty fast. And now let's see, we are talking about zettabytes, right? Zettabytes, any idea how much zeros are there? I think it's 21 zeros are there. That's humongous amount of data. And who needs this zettabyte kind of data, right? The first thing is that we have to see within, like we have lots of autonomous vehicle, kind of R&D happening around. Have any idea like how much amount of data it generates? It's around 5 petabyte of data in 8 hours. Each time that car goes out and comes back, it generates that amount of data, and that need to be stored, analyzed, and you have to fed it back using your AML systems, right? So you need to store the data, you have to process the data. So there are various requirements like smart cities. There are n number of things within we have to see, and you can have to see outwards also these days. So this particular picture, what you're seeing there is basically a black hole, which is called M87, which is 55 million light years away. Okay. So just to take that picture, can you imagine how much amount of data is spent? It's almost 8 petabyte of data from various radio telescopes is harnessed just to create that picture. Okay. So just imagine if you want to do more of that, how much amount of data you need and how much it will stack up. Now this is you have to see inwards also. This is a pandemic situation. We are all worried about when the vaccine will come out, right? So that kind of R&D also need to happen, but that requires a lot of space. Just imagine one whole genome from a human body is requires 150 gigabytes of data to save that string basically. Imagine for the whole world how much amount of data is required. So zettabytes of data is nothing. I think by 2025 we'll generally reach around 200 zettabyte of data, and now itself we already reached around 3 to 5 zettabytes of data worldwide. Okay. And what are the consumption models? Who is generating data and where it is stored? Generally the data is generated in edge systems. Basically you can see the energy systems, your transportation system, your mechanical hands, Surveillance, that's another important part. You might have seen this contract contact tracing and those kind of things that will be very helpful with video surveillance. But these data need to be saved somewhere, right? Many of the data will be saved in the system itself, but they will have a very limited capacity, right? So that data need to be pulled into core systems where the data will be processed, and possibly it will be fed back to the system for better performance or better whatever, right? Just imagine in a surveillance system, you want to search for some person worldwide. It's pretty much possible, right? But processing is not possible in your camera. That data need to be fed to a core data center. Probably the data will get figured out there and figure out who's the person, and they can push that data into the camera so that it can have a high resolution image of that particular incident, something of that sort. So you act you basically harness things in a global scale and act in a local scale, basically. And another aspect is multi-cloud. There are lots of clouds available now, this cloud, that cloud, private cloud, public cloud, all these things are available. All are silos, basically. If you want to move an application from one cloud to another, that might not be that easy. But that's something which we need to think about. So add all your studies and other things into these aspects to make the world better place, basically. So with that, if you have any questions, you can ask me, or you can type it in your chat box, or you can send it to me as well. So I would have some advice to you, basically. So generally, figuring out problems, that's important. Any system, figure out some problems, and if there is a problem, come up with solutions. You can use all your data structure, algorithmic, all those skills into that, basically. And that's one aspect of it. So finding a problem, solving it, that's one. But finding the problem is more important. When you know about a problem and you are searching for a solution, you are basically an engineer, right? But if you are searching for problem and figuring out the value of that particular problem, that will make you an entrepreneur, basically, which is what is we require going forward mostly. We will definitely need good engineers and entrepreneurs too, basically. With that, I would like to stop this particular webinar session. Thanks for attending, and if you have any questions, please ask.
Yeah, thank you, Tommy sir. Thank you for the wonderful session. I think we have some queries in the chat. Can you answer that?
Okay, one second. Let me open that. Okay.
There's a query from Rupa Keshavan, CSE.
Yeah, I'm going through that. So okay, sir, shall I place a query? Okay, what type of efficient computer systems can be suggested for utilizing ZTAB? Okay, so all these systems are generally used. So scale is very important for ZETTABYTE kind of storage, right? So again, depends. I showed you one slide, the criteria of selecting a storage for a particular kind of application. Let's say your application, what is the demand, basically, what kind of scale it needs, what kind of latency it requires. Imagine a railway ticket booking system. That's a simple example. Let's say your Tatkal is just opening up. You just want immediate response, right? It cannot be like milliseconds or anything. That will end up in seconds or multiple seconds in your application, right? So there you might want to use a block system, right? In fact, they'll be using a block system for that. But let's say in Facebook, if your photo is showing up in 1 second, that is fine. There you will be using an object storage system. And if you want to use some file sharing, if you want to share some files or anything with your friends or anything, you want to use a file sync and share kind of, there you will be using a file system kind of thing. So it again depends on a system. Every system is efficient, but again, there are criteria. And the other criteria is like money, right? The expense for a bit. So that's very very important in a enterprise world. Hope that I answer your question. And for high scale, object storage is the way to go. And generally what happens these days is like you will have tiers. So you will have your block or high performance file systems for your driving your AML workloads. But there you will keep only the subset of your data, not the entire data set. Only the subset that you are working on, you will keep in that hot tier. That is the tiering aspect. And all other data, your data lake, all those kind of things, you will keep it in the lesser, higher capacity, lower cost media. Hope that answers. And
some other questions are there.
Okay, I'm scrolling through that.
Okay.
Can you read it out? I mean, yeah. Okay.
And there is a question. There is a difference between big data and data science.
Okay, so basically big data is basically the unstructured data, because see, generally what an application do in olden days, what they do is like mostly they will have it in a database like Oracle or something of that sort, right? Where you have structured data, meaning you have definite fields, okay, name field, your ID field, those things are there. But nowadays that's not the case, right? There are so many things, and like you will have your photos, you have your PPTs, you have your doc files, you have some other kind of files. So many things are attached to you probably, right? So that's an unstructured data. So the collection of unstructured data and the structured data is collectively called big data. And that is your data basically. Now that data need to be analyzed by somebody, right? So there are multiple aspects. One is AI, which is artificial intelligence, and another one is machine learning, and there is one more thing called analytics. Analytics is basically you do the entire data you have and you want to find some insights from that. Let's say you are a CEO of a company, you have tons of data out there, but you just want a specific metrics. You are not going to search the entire thing in your big data set, right? So subset of data, you do the analytics and just give a dashboard kind of thing. That's basically the analytics parts. And AI/ML, basically ML is basically machine learning. You train your systems. Basically you give a subset of data and say that, okay, the machine should act according to, okay, if this is the input, this is the output, like that. Let's say for example, you give 10 pictures of dogs and train that model to figure out what is dog. Then that mechanism you have to write. Basically now it will see what are the aspects of dog, and let's say you give a picture of cat, that trained model will figure out, okay, the cat doesn't have the features of dog. Now it will analyze it as not dog. It will not analyze it as a cat, but it will analyze as a not dog. And artificial intelligence is one more step basically. Okay, so it basically machine learning, you have to train your system, but in artificial intelligence it's one more step further ahead. It itself will learn like a baby. How does baby learn language and all? So like that it will learn from its mistakes and it will go forward. So these are the different aspects of AI/ML and the difference between big data.
Sir, another one question is there.
Okay.
Can you give some research topic in this?
So everything is a research topic in this. So you take one of the field, I mean any field basically, you can actually find problems in the current implementations. You can always find issues in the current implementations and you can always go forward. So in the trends, what I have shown is that high speed storage systems, right, NVMe and similar, that's one area of research currently going on. And another set is basically in the field of self-service, basically as a service. Everything we want to showcase or provide as a service kind of thing. So lots of things has to go inside that. And in that hierarchy you can see how fast you can access data. That's the key basically. So and the aspects which I told, the enterprise features, right, you take any enterprise feature in that, you will find thousands of possibilities to enhance it. So all those fields are better for your research.
Sir, another one question is from Pranav K. How efficient is cloud storage?
Cloud storage is efficient from availability point of view. It's highly available, and if you consider, let's say, if you are a startup kind of place where you don't have much money to invest to buy hardware, right? So there you can start low with public clouds. It's pretty cheap. Whatever you consume, you spend the money, right? So that way it is pretty easy. But let's say if you have a humongous amount of data and huge number of operations to be performed on that, cloud might not be a good option because of the cost aspects, because you need to see the cost aspect as well. But otherwise cloud is highly available, and it is available throughout the world. Need not be you have to be connected to that particular system, right? It's connected to internet, so it's accessible anywhere. So that's the beauty.
Another one question is there. Can you explain a little bit about Hadoop?
Okay, Hadoop is basically like a big data processing system. If you want to run this map reduce kind of thing, like for this machine learning and all, even for artificial intelligence, there should be, that's a specialized field basically, where you have tons of data in a data lake. Now you want to do some kind of ETL processing, or you have to do map reduce on top of that. So that's basically Hadoop is a collection of things basically. File system is one, Hadoop FS is one, but you have other things on top of that, like Spark. You will use that for your map reduce work. Hive is there, and there are many databases available on top of that. So these things essentially do map reduce kind of task. As I given that example of identify dog from n pictures, you will be doing something of that sort. So Hadoop is an ecosystem, and there are many players starting from open source. You have Apache will give all these softwares like Hadoop, Flume, Scoop, Spark. All these kind of things will be given by Apache. It's readily accessible for you. You can actually install these things in your laptop also if possible. And there are enterprise players as well, like HP. We have a platform, something we just released it. We call it as HPE Esmeralda, which is the platform we just released a week ago, which can do AI/ML in a Hadoop kind of environment. That's one subset, but we provide a containerized orchestration on top of Hadoop or general storage systems. Basically, you can actually browse through some of those things. It will give you more aspects.
Sir, another one question is in chat. It is a little bit bigger. Can you go through it?
Okay. 1 second. Okay.
By Suraj
which would be your top 3 open source and proprietary file system would be usable? Okay, open source basically, again I showed various mechanism. One example I showed is Ceph, which is kind of very promising, though currently the performance is not that comparable with the industry standard offerings, but scalability wise and the kind of feature wise, that's a very good one. So Ceph is good. Then there are other offerings as well, like MinIO, Scale.io. This gives object storage. It's open source again. Then OpenEBS, it will give open source block kind of access. So all these source code are available. So you just need to go to GitHub and get these source codes. And proprietary, I can talk about HP. I cannot talk about other companies because I might be liable for that. So for HP, whatever solutions are available, I had given. So for block storage system, we have tier 0, tier 1 storage, which is Primera, 3PAR, and Nimble. And for file system, we have File Persona for 3PAR, and we have scale out storage from our partners, which is Cumulo, Cohesity. Then on object storage front, we have again from partner side, we have Scality, we have Cloudian. We have again cohesity, providing the object storages, which is very highly scalable. And from enterprise point of view, if you want to use AI ML kind of workloads in a containerized way, HPE Ezmeral is the going forward platform. And so that's one model. You can buy the hardware. There is one more model called HPE GreenLake. That's a consumption model. This is like a cloud kind of as a service available in on-prem basically. So GreenLake, HPE GreenLake, maybe you can browse. So what all features which I told on block, file, and object, you can access it as a pay-per-use model or pay-as-you-go model in HPE GreenLake, and you can increase your capacity just like cloud.
Yeah. I think queries in the chat session is over. So any participants, do you have any other queries?
Guys, don't be shy, you can ask. Generally, I know, see, I was also just like you 17 years ago. I mean, I used to be like silent. But again, you should open up. And now the thing is that you have lots of avenues to gain knowledge, because internet is available there, and there are tons of open source things out there you can access. Only thing is that you just open up your imagination. That's the only thing.
Yeah. So participants, can anyone share your feedback? Please switch on the mic and share your feedback. Someone please share your feedback. Yeah, another one question is there in the chat. Lifetime of SSD device.
Okay, so that again depends on various factors, how you use your SSD as well. So basically there is a mean time before failure which will be marked for any SSD. But again, the SSD will be marked for something called drive write per day. So if you use a drive which is marked one drive write per day, and you started writing at least the entire, I mean the capacity, let's say 1 terabyte. If you're writing 3 terabyte every day, then your lifespan will reduce by 1/3. So these are the two aspects you have to see. Mean time before failure, that's one. That's your NAND thing. And your drive write per day. These are the two things which you need to see. And again, depending on the NAND flash used in your device, it can have different kind of I mean lifespans. So you have different kinds: MLC, SLC, MLC, QLC, TLC. So QLC is kind of new ones which can have a very high capacity, but you cannot drive a lot into that particular drive. Okay. So again, depends on media. There are various levels, but again, lifespan will be like it's more actually. It's like 5 years definitely it will. And hard disk is actually persistence is best with the hard disk, because SSDs inherently, if you see electronics components inside that, it requires frequent refresh of your NAND cells basically. So if you keep your USB drives or SSDs for a very long time without connecting to any system, there is a fair chance that there might be data leak, right? But hard disk, you write once and that will last for what? Ages, maybe 100 years, 200 years, like that.
I think, sir, another one question is on chat by Suganya.
Yes.
Can you go through it?
1 second.
NVDIMM.
Can you read it out?
There is a difference between NVDIMM P and NVDIMM N.
Okay, as I told, so basically the NVMe, there is a form factor like this, similar to our DRAM, right? DIMMs basically. So there is a form factor like that, and actually you can keep NAND inside that, high speed NAND inside that. And so if you go to slide, One second. Okay, so if you go here, able to see. Okay, so NVDIMM N is basically nothing but it will act like a DRAM. That's a persistent DRAM, and your access is basically in bytes, just like in DRAM. So you write some bytes and you read in terms of bytes. But in NVDIMM P, the same device, or it would be a different device, but the form factor is same, and there you will be writing data in terms of blocks. And NVDIMM P, you will be basically having block interface, like block interface or file interface basically. So you will write in terms of that, not like you cannot simply dereference that particular memory location in your program. You have to do read or write. So that's the basic difference. But the media used is NAND, and probably in NVDIMM N, probably you will use some kind of super capacitor also to make your DRAM capacity inside that also persistent.
Okay, I think it's time is also going on, so we can go for a conclusion session. Thank you, participants, for your patient listening, and thank you, Tomy sir, for your wonderful session and for your query. Now, another one thing to the participants, we will share the video of this webinar through our YouTube channel. We will mail you the link and everything. And now I invite Manish Manoj to hand over the conclusion section.
Thank you, Fepsin, sir. So, first of all, I would like to thank our resource person, Mr. Tomy AC, Solution Architect, Global Sales Engineering, Hewlett Packard Enterprise, for making us aware of storage systems and all the associated domains. Thank you, Mr. Tomy, for giving us a greater idea to the GBs and TBs of data that we use today.
Thank you.
I would also like to thank Mrs. Sunita K, Senior Architect of Hewlett Packard Enterprise, for connecting us to our resource person. Next, I would like to thank the management of my college as well as the Department of Computer Science for making us able to organize a webinar like this. Also, I would like to thank Mrs. Ashwati Wilson and Mr. Binish M, Staff Coordinator of CSI, and Mr. Fepsin Adishmon, Staff Coordinator of CESA, for organizing this wonderful webinar. Next, I would like to thank all the wonderful participants for listening and participating in the Q&A session. And I hope that we could see you all for the upcoming webinars from our side. Thank you all. Thank you, sir.